Well, one, did you write down the derivation that I'm talking about in your notes? Do you see it in your notes? So what variable was solved for? V. Okay. We solve for V. Why? Because we want to get this in other words. You know, is there a different way of looking at this equation? Yeah. Well, we can't solve the ideal gas law for mass, but we can solve it for V. V is equal to nRT over P. And then we'll plug that in here for volume. So the mass is equal to nRT over P. And then when we divide by a fraction, we invert and multiply. So this is going to be the mass times P divided by nRT. But we didn't stop there. You have to recognize something. What do you have to recognize? You have to recognize another definition. The definition of molar mass. The definition of molar mass is what? Mass over moles. Do you see mass over mole? Yeah, we see mass over moles right here. Mass over moles. There. And so mass over the moles is just the molar mass. It's grams per mole. And so we'll plug that in here. It's the molar mass times P over RT. So we don't have to do any experiment. If we have a known gas, then we can easily determine its molar mass from the periodic table. We get the molar mass from the periodic table just by adding all the weights. And then we can determine the pressure, we can determine the density at any temperature and any pressure we want. We have zero experimental work we have to do. So here it's asking us what is the density of helium at 22 degrees C at 744 torr. We can easily determine that using this. And so you either have, well, the density is going to equal the molar mass times P divided by RT. Okay, so let's go ahead and do that. What is the molar mass of helium? The molar mass of helium, I'm going to get it to 4 sig figs this time. I'll just stop over here at 4.003. The reason I didn't get it to 4 sig figs in that calculation is I just wanted to do this one in my head. Which I could do. It's 1/4. 4.003, and it didn't make a big difference because I was only given 2 sig figs. Somewhere. And so we've got 4.003 grams per mole times the pressure. However, the pressure is wrong units. So do I want to memorize a new equation? No, what I want to do is I just want to get all my variables in the same units as my equation. And so what I'm going to do is I'm not going to do a separate calculation. You know, earlier I did a separate calculation. And this one I'm just going to do it here. I have 744 torr of pressure. And so I need to convert this into atmospheres. And so 1 atmosphere is equivalent to 760 torr. And so the torr cancel, and that gives me atmospheres. So I have my pressure in atmospheres, and then I know my R. What is my R value? 0.08206 liters times atmosphere per mole times Kelvin. And then my temperature is 22 degrees C, which is 295 Kelvin. That's it. And so let's make sure all the units work out. This is a quick check because I might have made a mistake in the derivation here, but we can easily see if you make a mistake because the units won't work out. So let's see, the moles cancel here. The atmospheres cancel here. The kelvins cancel here, and that gives me grams per liter. Well, that's density. Density should be grams per milliliter or grams per liter. Normal densities are in grams per milliliter, but for gases are 1,000 times less dense typically, so we want them in grams per liter rather than grams per milliliter. And so the units work out, so the equation that we derived looks good. And so I'm just going to take in the numbers here. 4.003 times 744 divided by 760 divided by 0.08206 divided by 295. 0.1618. So I get 0.1618 744 torr, 36 jigs. So 0.1618 grams per liter. It's very low density. Low density. All right, so let's take a look. So what did your book do? Book does this. It converts the Celsius temperature into Kelvin. 22 plus 273 gives me 295 Kelvin. Pressure is 744 torr. The density equation, I'd like to use lowercase. Your book likes uppercase, capital. Density is equal to molar mass times P divided by RT. So we have molar mass times P divided by RT. The same equation, that's good. Molar mass, they use the same 4.003 grams per mole. P, 744 torr. But you take a look at this, they did it differently. For example, 62.4, where did 60, did we have 62.4 somewhere? Where did 62.4 come from?
Try 127.4 divided by 760, that might be it.
No, 744 divided by 760 is going to come less than 1. Yeah, that's 62.4. Do you know where that came from? This is another thing I don't like about your book. There are a lot of things I like about your book, but and a few things that I don't like. This is one of those few things that I don't like about the book. I don't like that the book makes you remember a lot of variations of the same equation. These variations aren't that useful like the previous one that they showed you. And two, they like you to remember a lot of different values of R. You know where 62.4 comes from? That's another way of expressing R. I only like to memorize one R, 0.08206 liters times atmosphere per mole Kelvin. That one. But what they want you to do is they want you to remember other ones. So for example, if the pressure is not in the atmosphere, so let's say the pressure is in torr, then it's 760 torr per atmosphere. And the atmospheres cancel, we got torr. And so this is going to come out to 760 times that. What is 760 times that? 760 times 0.08206 is equal to 62.36. We're allowed 4 sig figs here. 365 liters torr per mole Kelvin. Liters torr per mole Kelvin. So 62.4 liters torr per mole Kelvin. That's what we got. Do you want to memorize this? Because this is the one for torr, and then we have another one for PSI. We have another one for whatever pressure units you want. And then we have ones that are for milliliters. No, we don't want so many variations. The easiest thing is if you got torr, then convert it into atmospheres. Don't bother memorizing a whole bunch of different R's, and your book gives you a whole bunch of different R values they use. So 62.4, that number doesn't register in my mind at all because it's not one I'd bother memorizing. Anyway, we'll get the same answer, of course, which is 0.1618, which would round to 0.162. Okay, I'd like to show the rounding step, which your book doesn't like to do. so that was a special calculation. Density is one. The molar mass of an unknown gas, probably not going to use that. Density, yeah, that's pretty useful. This one, though, is pretty useful. Molar volume. Let's see how they derive the equation for molar volume. First, what is the density of molar volume? The definition of molar volume. The definition of molar volume is, how many liters per mole. So if I have a mole of gas, how many liters? So volume over n. So how did they derive it? They derived it maybe an easier way than I derived it. Remember how did I derive it? Well, I don't know if they did it the easier way. What I did was, can you look back and see what I did? How did I derive the equation for molar volume? I think the alarm might go on shortly. Maybe not. We solve for n, right? But we could solve for n. N is equal to PV over RT, or we could solve for V. Both of these are for the gas. What did your book do? Your book solved for the numerator rather than the denominator. The reason I solved for n was just to keep it consistent. I solved for the denominator of each of the ones I derived, right? And so your book solves for V and then substitute that in here, and then we end up with this equation. I solved for n, substituted it in there, and ended up with the exact same equation. So it doesn't matter. You could solve for n or you could solve for V. There's yet another way to do this one. Let me just show you one last derivation for molar volume. The one last variation of solving this is straight from the ideas. PV equals nRT. So what I'll do is I'll divide both sides by P and N. If I divide both sides by P and N, I'll get V over N is equal to RT over P. Well, P over N is the definition of the molar volume. So this is equal to the molar volume. That's the other way to have done it. Now, nonetheless, we want to know the equation for molar volume. Molar volume is very useful. Probably molar volume is the most useful out of all of this special calculation. Molar volume would be 1 and density would be 2. The molar mass of an unknown gas. But one thing is, this gas has to be known. This has to be a known gas because we need to determine its molar mass. And therefore, we need to know its formula so we can calculate its molar mass based on the molar masses in the periodic table. All right, so here's an example of a molar volume calculation. Well, we have the equation here. Molar volume is equal to RT over P. And so we need T and P. That's it. And so at the common reference conditions of standard temperature and pressure, standard temperature is 0 degrees C, and standard pressure is 1 bar. At standard temperature and pressure, we just plug it in. Here I would use 0.08206. Carbolyci uses this. The only reason I want you to memorize it for 466 is that's what you'll need in Chem 1A. In Chem 4, you probably can get away with 366 here. And if you're going to memorize it, you might as well memorize it for 466 now rather than later. And so, okay, we put in R, we put in the temperature. Temperature is 273 Kelvin, 0 degrees C. And then we divide by the pressure. The pressure is 1 bar. Then we have to convert the bar into atmosphere, so this is good. This is funny because But here, they're using their standard R. They didn't use the R that's expressed in bars instead of atmosphere. So this is the way I would have done it too. I would have just converted bars into atmospheres. The conversion of bars into atmospheres, I know this. 2 more sig figs. So let's look at the molar volume. The molar volume at RT is 298 and 1 atmosphere. Room temperature 1 atmosphere. The molar volume is equal to 24.45 liters of gas for every mole. We did this calculation earlier. This was my example calculation. But this is expressed in atmospheres. So the first example calculation, we're going to come to this in a minute, but the first example calculation is, that I'll do on the board here, is the molar volume at RT. We'll have 298.15 Kelvin in this case. 298 or 298.15. And 1 bar. So what's bigger, a bar or an atmosphere? You know what's bigger? A bar, 1 bar or 1 atmosphere? Which one's higher pressure? 1 bar or 1 atmosphere? Well, we need the conversion factor for that. So let's do that over here. As an aside. It turns out that 1 atmosphere is equal to 1.01325 bar. This conversion factor comes from chapter 4. Let's go back to chapter 4 here. It's not chapter 4, let's go back to chapter 4 here.
So it's not the same for the sig.
It's very close. When you look at it, they aren't the same, but they're very close. Almost the same. But which one's slightly bigger? 1 bar or 1 atmosphere? 1 bar or 1 atmosphere? Which one's slightly bigger? 1 bar? 1 bar is bigger than 1 atmosphere? It turns out what's slightly bigger is the atmosphere. The atmosphere is slightly bigger because you need more than 1 bar to make 1 atmosphere. And since you need more than 1 bar to make 1 atmosphere, the atmosphere must be bigger. In fact, the bar is going to be less than 1 atmosphere. And so 1 bar is equal to, we'll divide both sides by 101.32. So it's 1 over 101.325 atmospheres. So 1 divided by 101.325 is what? 0.9869. 0.98692. I'm about 6 sig figs. 2, 3, 2 atmospheres. And so 1 bar is slightly less than 1 atmosphere. Slightly less. That conversion factor comes from this. The conversion factor is a little weird because from physics we know that 1 atmosphere is equivalent to 101,325 Pascal. So this is back in chapter 4. Go back and look. And so what is a Pascal? Well, it turns out that 1 bar is defined as 100 kilopascals or 100,000 Pascal. So 1 bar is 100,000 Pascal. Pascals, that means that 1 atmosphere is equal to 1.01325 bar. That's the conversion factor. Atmospheres bar. We would have to derive that from this, or do 2 conversions together. Okay, going back to this. Let me just show you what we're doing here. Going back to this, we did a molar volume calculation earlier. Here. This is why molar volumes are so useful. This equation, let's ignore this here. This equation says 1 mole of oxygen plus 2 moles of hydrogen yields 2 moles of water, gaseous water. And so 1 mole of oxygen, how big is that? Well, how big that is this. At room temperature in 1 atmosphere, it's 24.45 liters, or about 24.5 liters. So this is why I said 24.5 liters earlier. 1 mole of oxygen is 24.5 liters. So this box would be 24.5 liters if you filled it with 1 mole of oxygen. 2 moles of hydrogen would be twice that size, or 49 liters. 2 moles of oxygen, 49 liters. But if I change the pressure, that's going to change the volume. And so rather than looking at a pressure of 1 atmosphere, I'm going to look at a pressure of 1 bar. Is 1 bar greater pressure, or is 1 bar less pressure? 1 bar, is it greater than 1 atmosphere or less than 1 atmosphere? Yeah, actually 1 bar is less than 1 atmosphere. And so if I do 1 bar instead of 1 atmosphere, the pressure is reduced. If the pressure is reduced, what's going to happen to the volume? Volume can expand. And so if I reduce the pressure, gases expand. If I increase the pressure, gases contract. And so I said that, okay, this is 24.5 liters of the pressure of 1 atmosphere. Now, if I change the pressure to 1 bar, that's just slightly less pressure. It's slightly less pressure. That means that this volume should change a little bit. And if it's slightly less pressure, I expect the volume to increase a little bit. But let's go ahead and calculate it and see what it comes out to. And so I need the equation for molar volume. Molar volume is equal to RT over P. Either I derive it or I have it memorized. R, I only want to memorize 1 value of R. I don't want a whole bunch of values of R. So I don't care what the value of R is in torr. I don't care what the value of R is in bar or whatever else. I'm just going to use 0.08206 liters times atmosphere per mole times Kelvin. Okay, temperature always has to be in Kelvin, 298.15 Kelvin. The pressure is going to be 1 bar, but that's the incorrect unit. I need it in atmospheres. And so all I'm going to do is I'm just going to convert bars into atmospheres. And so I'm going to use this one because this is the one I remember from physics. This one I don't use. And so I know that 1 atmosphere is equivalent to 1.01325 bar. Now I can round it because that's 6 sig figs, you know. I only have 4 sig figs here. I can round it, but I'm not going to bother rounding it because it's an extra mental step, and since I already have it memorized. You don't have to memorize it, but since I already have it memorized, we use the whole thing. Just like this. I'm not going to bother rounding that to 3 sig figs. It's just going to mean my rounding error is going to be bigger. And so let's see what it comes out to. So 0.08206 times 298.15. Okay, I divide by fraction, so I'll invert and multiply. Times 1.01325. 24.790. 24.790 liters of gas per mole of gas. And so this would be the molar volume of gas at room temperature 1 bar. And so what happened is the bar is a little bit less pressure. It's a little bit less pressure, so the volume of the gas expanded a little bit. You see it went from 24.45 to 24.79. And so if I redid this problem in bar, and so I'm at room temperature and 1 bar, then it would read like this. 1 mole of gas, O2 gas, would be 24.79 liters, or about 24.8 liters. Let's go with 24.8 liters. And so this would be 24.8 liters of oxygen combined with how many liters of hydrogen? 24.8 liters of oxygen plus how many liters of hydrogen? 49.6 liters of hydrogen would give me 49.6 liters of gaseous water. That would be in bar. If I read this as 1 mole plus 2 moles yields 2 moles of gas. All right, so we either work in atmospheres or bar. If we work with atmospheres, then it's 24.45. I've actually memorized this number. It's a useful number to know. If we work in bars, slightly less pressure, it's going to be 24.79 liters per mole. Now, if we work under conditions of standard temperature and standard pressure, what is it? All right, so standard pressure is 1 bar. It's the same as this. But what is standard temperature? Standard temperature is 0 degrees C, 273 Kelvin. And so, under standard pressure, which is 1 bar, and room temperature, it's 24.79 liters per mole of gas. But what if I cool it down? If I cool it down from room temperature to 0 degrees C, will the volume expand? Will the volume contract? Or will it stay the same? It'll contract. And so what's going to happen is, if I take this and cool it down to 0 degrees C, it's not going to freeze because it's not water. But if we cool it down to 0 degrees C, what is the molar volume? 22.7. And so the volume contracted 22.7. And so we go back to this slide here. If I did this at 0 degrees C rather than room temperature, then 1 mole of O2 occupies 22.7 liters. 2 moles of hydrogen would occupy 22.7 times 2 is 45.4 liters, and I form 45.4 liters of gaseous water. So your book asks you to memorize one of these numbers. Should you memorize? Well, let me tell you the old STP. The old STP was 0 degrees C and 1 atmosphere. At 0 degrees C and 1 atmosphere, the molar volume. I had this memorized. I've had this memorized since I took Chem 4. In Chem 4, I had to memorize this. So I worked hard at memorizing this number. So hard, I've never forgotten it. 22.4 liters per mole. At the time, it was very important. Everybody memorized this. So everybody was memorizing. All my classmates were memorizing. At the new STP, the molar volume is 22.7 liters per mole. And so what's the difference between the old STP and the new STP? The old STP used atmosphere, the new STP uses bar. And a bar is a little less pressure. If it's a little less pressure, then the volume expands a little bit. Right? That's what we see here. So out of these four numbers, Krakalici says to memorize the new STP. Memorize 22.7. But let me tell you something. I memorized the old STP, 22.4. Never forgot it. But how many times do you think I've used it since I took Chem 4? 0. So I thought, what a, complete waste. Because I have limited memory. Complete waste. I'd like to forget that number, but I can't. It's like one of those songs, you can't forget it and you want to forget it because you're tired of it. I'm tired of 22.4, but I can't forget it. It's like a curse. There's so many other things I want to remember that I can't. But anyway, out of these four, which one do you think you want to memorize? 24.45, 24.79, 22.7, or 22.4? Which one of those do you think would be the most useful? Yeah, either of these two would be much more useful to memorize. And so I have this one memorized, but it depends. It depends. The atmosphere is like a US unit. The bar is like a metric unit. And so it depends. I think, if we're going to be using bars, this one would be much more useful to memorize. All these others. 24.79. So I wouldn't even bother memorizing it. Well, it's interesting to see, the colder temperature. And the reason is how many laboratories are set up for standard temperature and pressure? Not very many. In fact, I don't know of any. Never worked at one. A lab where the room is set up at 0 degrees C. It's terrible. I would hate to work in that lab. But a lab that's set up at a room temperature, most. And if you're dealing with bars or atmospheres, well, they're so close.
When they do stem cells, what do they use standard pressure?
When they do what?
Stem cells.
Stem cells?
In the laboratory?
No. They do it under, if they do stem cells, there's one more condition, which I haven't talked about. Have you heard of the biological standard conditions? There are a couple more restrictions, but since you asked, I better answer your question. Except, these are what we call thermodynamic conditions. And so there are more that are going to be for this is from Yahoo. Yeah, be careful of Yahoo answers. Some of the answers that are provided in Yahoo answers are way out there. It's not reliable at all. Wikipedia has been pretty reliable. All right. All right, standard pressure, 10 to the 5th pascals. 10 to the 5th pascals is the same thing as 100,000 pascals, which is the same thing as 1 bar. And so standard pressure is 1 bar. All right, strictly speaking, temperature is not part of the definition of standard state. However, for gases, we have this standard temperature in gases, which is 273.15. But this is not very useful. And so what I do is I like to use this. We don't call this standard temperature, we call this room temperature. Room temperature is 25 degrees C or 298.15. But for biologists, it depends on what type of biology you do, but biologists, what do you think the temperature they use? They don't like to use room temperature. Yeah, they like to use body temperature because the temperature influences, how the structure. We talked about structure already, like, tetrahedral, this or that. But it turns out that the structure of a lot of these proteins depend on the temperature as well. And so if you keep increasing the temperature, what can happen is it upsets the structure. It's what we call denature. Denatures the protein. The structure kind of breaks apart from what you expect. And so the structure that we want to know, what is the structure at body temperature? That's the structure. Because if you start changing the temperature, the structure changes as well. Certain angles and this kind of stuff. So biological standard conditions would be something like 1 bar and body temperature.
So that's Gibbs-Dale.
Well, but it also depends on what they're trying to do, I would imagine. I don't know about stem cells specifically, but there's something called biological standard conditions. I'm not a biochemist, but if you're going to pick one temperature, you would pick the temperature you use the most. I'm a chemist, so I want to pick the temperature I use the most. Do I use 0 degrees C the most? No. So how many people use 0 degrees C? A tiny, tiny fraction of people use it. So what's much more useful is room temperature. There are other parts of the standards. This is when you get into thermodynamics. You've got to talk about concentration and whatnot. Just to answer your question.
So Gibbs-Dale comes under biochemistry.
Yes, right, or molecular biology. I would think, I don't know. I mean, all those labels, they start to lose their meaning. Basically, as you get higher to higher level classes, the dividing line blurs. So, for example, are you a biochemist or you're a molecular biologist? Molecules, biochemist, molecular biologist. Or are you a physical chemist or are you a chemical physicist? The dividing line blurs. It just is that some people they approach it from a physics bias, other people approach it from a chemistry bias, and so it depends. So, like, are you a biochemist or are you a biological, chemical biologist or something like that? And so people who work with stem cells, you have all different kinds of people in all different kinds of fields. Not one field specifically. You have your straight biologist, you have your biochemist, you have et cetera, et cetera. Molecular biologist. I don't know. But it's not my area, so I don't know what they like to call. So let's take a look at the molar volume calculation here. I guess we're out of time since it's So I'll tell you what from chapter 14. This probably just going to be ideal gas. Probably the stoichiometry stuff we'll put on the next test. So we'll just have the first part of chapter 14 on this test. Just like this, since I haven't gotten to the second part. Yeah. But molar volume calculations, we just need the molar volume equation. Just plug it in here. There's a molar volume equation. We just need the temperature and pressure. So it's temperature and pressure. You can calculate the molar volume. All right, I'll stop here since we're going to end 10 minutes early. Just give them a break. We'll continue this tomorrow.